Okay, so I'm going to have a look at a problem like this that might be of interest to you. Um, so it's a beam that's already bent, and we're going to bend it some more by applying this bending moment down here. And we can see that it's a T-beam, so we've got a wider section at the top here, and then we've got this narrow section here. So this is our cross section. The things that I want to find for my T-beam will be, where's the centroid of this cross section? It depends which books you use, but the centroid is probably going to be written as a little r. I think I might go a little bit thicker. A little r with a bar on top. So that just means I'm just looking at this as a just plain cross section. Where's the center of that going to be? And it's going to be somewhere about there, I would guess. So that'll be the first thing I'm going to find. The second thing I'm going to find is called the radius of curvature, and most textbooks it might be given the symbol big R. So the radius of curvature is effectively the neutral axis of a bent beam. And it turns out because this beam is curved, or it's a curved beam I should say, because it's curved, then these two things aren't the same. So normally with a nice straight beam, your centroid and your neutral axis are going to be at the same location, but they're going to be at a slightly different location in this case. And for us, we'll probably find that this neutral axis will be a little bit below. So we'll probably find the neutral axis maybe there. So yeah, so those two things don't match up. And there's a sneaky little formula we're going to use to find that. And the last bit of my question will be to find, I don't know, I've got to find the stress somewhere. So I'm going to choose the stress at location A. Okay, so what's the stress at location A? That'll be the last thing I'm going to look for. My centroid, I don't need to look that up anywhere. I can memorize how to do that. So going to need some values, and I'm going to have that's the R0 distance will be 380 millimeters, and my W1, the width of the lower section, will be 21 millimeters, and the width of well, actually let's do the height next. Height of the lower section will be 130, and for the width 2 we'll have 75, and the height 2 we'll have 23. Do I need any other data? I need to know what this bending moment M is. So I'll set that to 1400 Newton meters. Rightio, I think that's all the data I need to solve these problems. So let's start off with where is the centroid going to be? So we imagine that distance there. Let's imagine that these things are lined up. It looks kind of they are. So this R0 distance, and this will be where I'm going to be taking my base. So that's my R0. Do you see that? So imagine this is where the cross section is. That's my base position, and I'm measuring that distance from there to there. So what's the formula we need for centroids? Well, remember it's like y bar, but we're using radius bar is going to be the sum of the areas. We're working in radiuses, so sum of areas times the radius of the section divided by the areas. So I don't think I really need to do anything else. I'll go and use my calculator. Right, so the area for the lower section is going to be, I don't know whether I should bother writing this out or not. I won't. Lower section will be 21 times by 130. So that's the area of the lower section. Where's the middle of the lower section? I'm going to let my calculator do all the work. So it's going to be 380. Now can I do the next bit in my head? I want to find the middle. Let's get rid of these terms. I want to find the middle of this section here. So it's going to be half of h1. Can I do that in my head? Half of h1 is 65. Okay, close the bracket. So I'm letting the calculator do virtually all the work. I could have put in 130 times 0.5 plus, right, now let's do the top section. So its area is going to be 75 times by 23 times by open bracket. So the first length we've got is the 380. The next length we've got is the 130. And then we want to get to the middle of H2. So that would be 22, 11 and a half. Yeah, is that right? So 22 plus 1, yeah, 23. Close the bracket. I think I would do this. I think I'll maybe put that at the top and then do the calc. So we got 2, 1, 1, 4, 4, 3, 7.5. Okay. 1, 2, 1, 1, 4, 4, 3, 7.5. Now we want to divide that by, oh, well, I've written it now, so I need to calculate it. We want to divide it by the area, so that's going to be the 21. Yeah, actually that's something worth doing because I'm going to use the area in my next calculation, so it's good to work out the areas. So 21 times by 130 plus 75 times by 23. So the area will be 4,455 millimeters to the power 2. So we've got our two numbers. Let's work out where the centroid is, and we're expecting it to be about here-ish, aren't we? So 4, I don't know, 480 maybe, something like that. Let's see if we get a number like that then. So 2114437.5 divided by 4455 equals 474 and 621. How many numbers do I really need? That should be enough. All right. So that's that. So the next thing is we need a formula for how you find the radius of curvature. I was looking at the lecture notes to see if I could find one. The the term that we use for, so that's my A. The term we use for that is given as, actually let's do a cut and paste so you can see it from the lecture notes. So it's this term here. So I grabbed this from, can't remember which lecture this is from, just. But, okay, so stop that. Right, so it's the area divided by the integral of 1 over all r. So r is a variable, so all of this radius is integrated that over the area. So that's quite tricky. And when it gets mathematical, we avoid it at all costs. So how we solve that is by having a lookup table, and this is my lookup table here. So we've got, I would imagine this is coming from Johnson. So we got these table results, and you'll see that how to solve this integral. So here we've been told that it is given by this term, and I'm getting a bit confused because the way Johnson has arranged the shape, this is your breadth and these are your two radial positions. So for me it's kind of like flipped around the other way, if that makes sense. So my R1 would be down here and my R2 would be here, and B is my distance there. I'm wondering, don't think I can move objects around. Let's just give it a go. Can I do that? No, I can't rotate it. Right. At least I think I can. Okay, so we don't work out the integral, we use this formula. And the next question is, what do we do when we've got a complicated shape like this, where we've got two bits? So an integration over an area can be split up into two integrations and joined together. So what we're going to do is we're going to use this formula basically twice. So we're going to say R equals total area over the integral of 1 over R for the lower section plus the integral of 1 over R for the upper section. Okay, so you can see that that is equivalent of saying the integral of everything over that section. But when I split them up as this, so I've got lower and upper, the advantage of splitting my integral up like that is I can now use the textbook solution of that integral and just plug in my numbers. So let's write out the numbers so you can see where the things are coming from. So the upper bit is going to be the area. So 4455. Obviously, I'm working in millimeters. Should have said that. And now use this formula here. So for the lower section, the width is my width is 21. Natural log. So R2 is going to be this position here where B is. So that's, I'll let my calculator do the work. 380 plus 130 divided by 380. Okay, so the next one to add on will be the top section. So that's going to have a width of 75. Natural log, right, so the lower R will be at that point B and the upper R will be at that point A. Okay, so the A point will be 380. I'm going to let my calculator do the work. Plus 130 plus 23. And the lower R, where B is, will be 380 plus 130. You can see how you're just dropping off that number each time. So let's stick that all into our calculator and see what we get. So let's try and do that in one go. 4455 divided by, right, so I've got my bracket. 21 times by natural log. And I'm going to need a bracket there. Oh, it's given me one already. Close that bracket. And I want to put another bracket in. Ooh, no, I don't want that. And divide that by 380. 380 plus 130. And is anyone going to answer that phone? Yes. Plus 75 times by natural log. Close that bracket. I want a bracket on top and I want a bracket on bottom. On top, I'm going to put in 380 plus 130 plus 23. And then bracket on bottom, I'm going to put in 380 plus 130. Right, so that gives me 469, and we'll do to 3 decimal places, 574 millimeters. Okay, so we've done part A and part B. It's looking reasonable. The neutral axis is a little further away than where the centroid is, which I think is what we should expect. Now let's find this stress term. So how do we do that? So looking at the lecture notes, this is what you got. I'm going to go to a new page. Right, so you got an expression like that. And you notice that this has got y's in it. So y is the distance from the neutral axis, which we found. So we got our T-beam like this. So we found the big R to be here, and relatively speaking, let's probably a bit longer, isn't it? And our centroid to be here. Okay. Well, we got this y. So y, notice, is, are we told where? The distance, here we go. Distance from the neutral axis to the point of interest. Right, um, so that is going to be where we're looking for. And we're looking for, so we've got our big R, so that's, I've got the right word. Yeah, big R. Big R is the neutral axis in effect. And we are going to be looking for the stress on the outer surface, which is where A is. Yeah, that's what I'm looking for. Right, so you can use that formula. I think you, however, have it in a different form in your short sheet, and I just sort of rearrange this, because the other way to look at it would be to say, you wouldn't have seen this in your lecture, but I rearranged it so it is looking like it's looking like this. So I'm substituted in that again. Let's look at our beam here. So you've got which way around was it? We've got our big R here and our little r here, and we've got our point of interest here, which is our y, and y is measured from the neutral axis here, okay, as opposed to the centroid. Right, now you can also say that your radius, which will be the distance, got to remember these centroids are being measured from here to here, wherever it's curving around. So we could say that if we take, okay, so that's R bar, sorry, should correct that, R bar. What's this R here? This R here is referring to the point of interest, okay? But in terms of where this datum is, so that, we'll give it to be a green. So that R is referring to that thing there, okay? So, how can I go from this R to this Y? I can see that it's something to do with this length here, big R. So if I take that big R, and then if I add it on the Y, I would not get this formula. So how does that work? Because my Y in this case is actually going to be pointing in a negative sense. So that's why we've got this difference of the Y there. So I should have Y pointing downwards, I think. Okay. Anyway, that's I think I've got that right. Let's double check. Yeah, so R is got a slightly different one there, but R notation. Yeah, y is pointing inwards, so that's why there's this negative term here towards the um, where it's being curved round. Right, so that's a minus y. We're going in the opposite direction. Y should be measured off in this axis. Right, so that's where this expression comes from. And so we are going to take this y take away r and this y here, and we're going to substitute in little r is big R take away y. What happens on top? You can see that you get y take away r there. So that ends up with a minus r on top. And then on bottom, we've got little y there. So little y we're going to replace with r take away have I gone wrong with my signs? I think I have. Or have I? No, I haven't gone wrong with my signs. Right, let's go back. Y take away big R. Y take away big R will be minus R. Then we got Y. So Y would be, oh yeah, I'm correct. So Y would be big R, take away little r. So I'm going to flip the sign there so that I'm going to get the minus and make that a minus big R. Too many R's. Right, so yeah, I'm happy that I've done that correct. Right, so the little r, to summarize, is the distance from where it's kind of curving around. So it's from this position to the point of interest, because I'm interested in the stress at A. The big R here is referring to the neutral axis position. That's the stress, obviously. That's the bending moment M. That's the A, because we've already calculated that, so we can use that. And what about this E term? So this not completely lined up there. So there we go. The E term here is this little distance. That's the difference from the centroid to the neutral axis. So we've got a little bit of distance there, and that, in my case, will be a negative value. Right. So I'm wondering if we're going to have any issues with signs being positive or negative and getting this the right way around. I would be tempted to be an engineer at this point and not worry too much about my convention. So here I've got the bending moment, and it seems to be doing a bending moment like that. on the bent curve beam. So that implies that anything sort of below my neutral axis here would be in compression, so I should be getting negative answers. Anything above this section should be positive, so I should be getting positive answers. So that's how I'm going to approach my formula. And I'm going to use this one here. So let's rewrite this. Stress equals M over E, where E is R bar. Take away big R. And then we want the area, which we've got. And then I'm going to bring up these terms here. So I've got 1 over R, big R, and that'll be a little r there. So let's put my numbers in. I'm expecting the stress to be positive because it's on the outer surface. And I have got 1400. What's the little r going to be? So come back to here. So to find the little r, that would be, because we're at this position, that would be all the r's acted. Well, that would be the 380, the 130, and the 23 added all together. So 380, 130, and 21, I think. So 23. Right. What about my big R? I need to go back to my first solution now. So big R is this number here, 46957. And we're putting the 4 as well. Rightio, so that's going to be positive, yeah, so we're going to end up with a negative here. Right, so I'm going to ignore that. So E is going to be oh no, I'm going to end up with the right thing. So I've just been talking a lot of bollocks. Centroid is further away than the radius of curvature. I got it wrong. What can I say? You're multiplying the effect on your outer curvature. There's going to be a bias away from the curve. Okay. Easy to convince yourself once you found the answer. Okay, so yeah, well, guys, what can I say? I was talking rubbish before. So, yeah, this is all going to work nicely. So we got the 474.62. Take away the 469.574. And then we want the area, so we'll use that number, which is this one here, 4455. and then we want the location, so that's 380. Right. Okay, so I've been putting these in as millimeters. Let's look at the units. I've got that is in SI units. This is going to be millimeters times 10 to the -3. And we've got here area times by length times by length. So times 10 to the -12. Yeah. Yeah. 1, 2, 3, 4. So we could make that times 10 to the 9. Let's do that. Okay, so let's put all of this stuff into my calculator. And what do I get? Whoops. So 7.4. And I think that's fine. So 7.4 megapascals. Right, so apologies for that. I did make a thinking error about which way round the centroid and the radius of neutral axis was. But my calculations are all correct. So I'm not going to reshoot the video. You can just have a laugh at me for being stupid.